So over to you, Sucheta. Hello, Sucheta. We cannot hear you. Sucheta,
She's, yeah, can you try to
is she
speak now?
muted?
Yeah, now we can hear you.
Can
Yeah.
you hear me now?
Yes, yes.
Okay, great. Yes, so I'm sure you all are having great time in this workshop. So today I will talk about how ultrafast magnetization dynamics gets modulated in the graphene cobalt gadolinium interface. So this work has been recently published in ACS Nano. Graphene is no doubt a wonder material, and like all of us are very familiar with some of its incredible properties, such as a tiny piece of graphite contains millions of graphene layers. It is an earth abundant material and also low cost. Just using a scotch tape, graphene layers can be peeled off and exfoliated on another surface. So this is a cheap and effective method of graphene exfoliation. As you all know, these sheets of graphene are very flexible. So they are integrable inside wearable electronics as well. Also, it is impermeable in nature. It is a zero band gap semiconductor with high electrical and thermal conductivity. So interestingly, it has many more applications and exciting properties that has been invented or explored over the years and in graphene based systems. So the radical idea of inducing magnetism into graphene has opened up basically the Pandora's box. Researchers have found that graphene maintain a give and take policy when it is hybridized with another material. It adds up new functionalities into that material, and some of its own property get elevated due to hybridization. Most importantly, the spin orbit coupling, which is weak for pristine graphene, becomes very strong when it is adjacent to another magnet. Also, reduction of magnetic moment due to proximity effect is observed. Graphene can act as a source of spin current via generation of spin current via spin Hall effect, Raspa effect, quantum spin Hall effect, etc. It can also channelize spin current in the basal plane of it and also across the c-axis. Graphene also can act as a sink of spin current. It can actually absorb the spin angular momentum from adjacent ferromagnet if there is a high frequency excitation. Now, in this next couple of slides, I will discuss optical generation of spin current and modulation of ultrafast dynamics in graphene ferromagnet interface. So in 2017, Sinha et al. Reported that time-resolved magneto-optical Kerr effect signal obtained from a nanoscale cobalt iron boron layer gets significantly modulated in presence of few layer graphene and graphite. Both the ultrafast demagnetization time in femtosecond timescale and remagnetization time in picosecond timescale, those are modulated. Also in longer timescale, for example, damping has been modified. They attributed this modulation to the p dehybridization between graphite and cobalt iron boron interface. The interfacial roughness also plays a role, and possible angular momentum transfer from ferromagnet to the graphene layer is reported. But more importantly, in 2021, Panda et al. Dug deeper and they performed pump probe measurement on CVT grown monolayer graphene interface with cobalt iron boron. So the thickness of cobalt iron boron varied from 1.5 nanometer to 6 nanometer. Due to bombardment of the ions on the sputtering chamber, the defect gets introduced in the graphene layer. And you can see the peaks relevant to the 2D bulk G and defect peaks from the Raman spectra. So they found that demagnetization time and damping are inversely proportional, which indicates presence of spin current dependent effects in the samples. So spin mixing conductivity that they have obtained experimentally is relatively considerably high, and it actually is similar to the heavy metals. So this seminal work very much confirms that graphene is a good spin sink material. So the next question remains that what happens if the number of graphene layers increases? So for that, we have exfoliated mechanically graphene layers on a silicon oxide substrate, and then we have cleaned the surface with acetone and IPA to remove the residue of the scotch tape from the surface. Afterward, single point Raman spectra is obtained on the flakes. We have identified micron-sized flakes with monolayer, bilayer, trilayer, few layer, graphene and graphite. The layer numbers are identified from the shape of the 2D peak and ratio between the intensities of 2D and bulk G peak. So there was no defect introduced during exfoliation, what we have observed from the Raman spectra. But after deposition of cobalt gadolinium 10 nanometer layer with 4 nanometer tantalum capping, we have found that defect peak arises in the spectra. So the ratio between D peak and G peak intensities reveals that the monolayer graphene accommodates more defect than the thicker layers, because the ratio is decreasing with increasing number of layers, which indicates that the defect density is decreasing consistently. To verify whether this is uniform or non-uniform effect, we have also done Raman spatial mapping on each flake, and we have found that the defect density is uniform, or the spread of defect is uniform throughout each flake. We have also performed atomic force microscopy measurement to confirm the layer thickness and surface quality after deposition of ferromagnetic film. The surface roughness is less than 1 nanometer. The thickness of graphene layers are determined from the line scan as well as the histogram estimation. Due to van der Waals interaction on the monolayer and bilayer surface, the measured thickness appeared to be relatively longer. It is larger relatively than the theoretical estimation of monolayer graphene, for example, 0.33 nanometer. The few layer and graphite flakes contains approximately 8 and 20 monolayers for our case. So in this slide, I will describe how the time resolved data looks like for bare cobalt gadolinium sample. So this ferromagnetic alloy is of great importance, as you all know, due to its tunable anisotropy and all optical switching properties. However, in our study, we have sputter deposited a 74% of cobalt with 26% of gadolinium amorphous film. This is in-plane magnetized and have not shown any complicated anisotropic behavior. So the vibrating sample magnetometry measurement shows that the magnetic moment is low due to nearly compensated moments of antiferromagnetically coupled cobalt and gadolinium sublattices. With this ideal film, we have performed time resolved measurement in non-collinear geometry, where 800 nanometer wavelength of probe is incident normally on the surface and polar Mach signal is detected. In presence of strong in-plane magnetic field, which also is little bit tilted towards the outer plane in order to provide the necessary torque to induce the precisional dynamics. So the full time resolved Mach spectra. So let me take the pointer option for a while. Yeah, so the full time resolved Mach trace is shown here. There are three prominent regime. One is the ultrafast demagnetization, then there is fast remagnetization, and there is slow remagnetization with precision. So from the Fourier transformation of the background subtracted precisional data, we have also obtained the high frequency peak, which lies between 8 gigahertz, and also this fundamental peak also follows the Kittel formula when we have plotted against the varying strength of magnetic field. So the damping we have extracted is about 0.3, which is a little bit higher than the traditional ferromagnets. However, it is in the line as ferrimagnets give. And the demagnetization time is about 300 femtosecond. So mostly the interaction is dominated by the cobalt sublattice. Now, this slide is very important. It shows that we have successfully probed the modulation of dynamics due to graphene directly in time domain. So what are the differences we can visualize or we can identify here? So first, the demagnetization time. This is the data for the bare cobalt gadolinium. The demagnetization time in presence of graphene layer, you can see that they are getting faster. Also, the fast remagnetization time decreases, and damping has a stark variation. So damping with respect to the bare cobalt gadolinium layer, if you compare monolayer and graphite, they are strongly damped or heavily damped. However, damping variation is not very prominent in case of bilayer, trilayer, and few layer graphene. The precessional frequency of graphite cobalt gadolinium interface also faces a rate shift, which means that the frequency is decreased. So that has been identified in the time domain as well, as I have pointed with the dotted line showing the period of the precession. So in the next slide, we will take a look at the quantitative changes of the dynamical parameters, which has been systematically plotted with number of graphene layers. So we observe that the fast remagnetization time reduces with graphene layer thickness, and in addition to electron lattice heat transfer in picosecond time scale, actually a defect or disorder assisted phonon scattering is taking place inside this system. So it reduces the carrier mobility, and it enhances the number of scattering center. So as we have already got some confirmation from the Raman spectra that there are structural defect present, also there can be atomic defects which can also change the structure of the Fermi level. So all those things should be taken into account. On top of that, monolayer graphene, if it is exfoliated on a polar substrate, for example silicon oxide, then polar phonon also comes into the picture. So they take away the heat from the region, and this is a heat transfer at faster time scale. It is taking place between the electron and phonon, and also different quasi particles in the system. So this is the reason behind why the fast remagnetization time has been decreased, or the process become faster. So in case of slow remagnetization time, the picture is different, because now the heat distribution is in longer time scale, and the heat is being distributed from the lattice of cobalt gadolinium to the graphite and the substrate, like in the surroundings. So this has been changed because of the thermal conductivity difference in different interfaces. So for clarity, we have considered 3 layers and 2 interfaces, where Kapitsa thermal conductance can be described as sum of 3 systems. One is the magnet, another is the graphite itself or the graphene, and also the substrate. So now in this pump probe experiment, one thing we have to keep in mind, that the heat transfer by the Gaussian laser pulse is non-uniform. So most importantly, for thicker graphite, the laser cannot reach the substrate. So thermal conductance of graphite along c-axis or towards the sample plane becomes very crucial. So we all know that the in-plane conductivity of graphene layers, it actually increases with number of layers. So as the conductivity increases, the heat is quickly distributed in the region. So the time is also less. However, in case of graphite, what we suspect is due to its bulk, volume, and also the non-uniform heat distribution in the region, the C-axis conductivity is playing a huge role, and that's why, and this is very low in comparison to the in-plane conductivity of graphene. It is thermal conductivity. So this, because of that, the remagnetization time is also getting slower. So the important parameter now I will discuss is the demagnetization, ultrafast demagnetization. So demagnetization time becomes 2 times faster due to hybridization between the pz orbital of graphene with d orbital of cobalt sublattice. More allowed states near Fermi surface is created, and it is very important to remind that coupling between spin and orbital degrees of freedom reduces demagnetization time. In addition to the spin current, can also play a role in the interface. So this collective phenomena from spin orbit coupling and the spin current, they modify the mechanism. And finally, the effective damping of this ferromagnet has shown a non-monotonic variation, because the spin current that is generated in case of that is absorbed by the monolayer and the graphite is high. We infer that their interface is much more transparent than the bilayer and trilayer and full layer graphene. So in case of bilayer and trilayer graphenes, there are also some backflow may occur due to the change in electronic and magnetic properties at the interface. So with that, I would like to conclude that the spin mixing conductance we have estimated is about 0.8 10 to the power 15 centimeter inverse, and that is close to the reported value what we have found from graphene. This will help to develop graphene based and rare earth magnet based spintronic devices in the future. Also, two-dimensional material can at some point of time replace heavy metals. However, I would conclude by saying this, that the scenario of spin current transfer or absorption is much more simpler in case of heavy metals. However, with number of layers in graphene, the scenario is quite complicated, but I would say from a positive note that it is very interesting also. So I would like to thank the groups that we have get support from is from Professor Jeter's group and Salahuddin group in UC Berkeley. And also I would like to acknowledge all the funding agencies, and thank you Professor Muduli and team for giving me the opportunity to take part in this workshop.
Thank you, Sucheta, for the nice talk. And it is open for questions. Okay, Sajid has a question. Yeah, Sajid, you
Yeah,
can go
thank
ahead.
you, Sucheta, for the very nice talk. I was wondering, do you have some proximity effect in your graphene? No?
Yes, we do have proximity effect in graphene, so that the data I don't have here, but the thing is, like, if you have proximity effect at the interface, the graphene actually gets some induced moment, and that causes reduction of magnetic moment at the magnetic interface itself. So as we have done some field dependent calibration of the frequency, there we have shown that the local magnetic moment has been modified, or it has been reduced due to this proximity effect, but that is very small in this film.
Okay. Thank you.
Okay, I think Pranab sir has a question. Yeah.
Sucheta, very nice talk. I was just wondering if you remember the work that we did with Professor Varman. There was this graphene when you deposit at different pressure, we were having some defects, and that was we call it defect induced spin orbit coupling. Mhm.
Right.
You know, and then that was scaling with, for example, DMI. But I'm just wondering, do you have such kind of defect in this spin orbit coupling in this system that you have? What do you think about that?
Yes. So for that, I would like to go back to one slide that shows that. Let me pull up that slide here. So if you see that the defects that we have characterized via Raman scattering, that is kind of increasing or monotonically varying with the number of layers. So it is low in monolayer and bilayer, and then it is high and it is decreasing with graphite. So if we remember this trend, that it has a trend with the number of layers, and then we take a look at the for example in this figure. So now in this case, the spin orbit coupling has effect on several dynamical parameters, but the spin orbit coupling in monolayer, which is extrinsic in nature, and the intrinsic spin orbit coupling of graphite itself is already elevated. So the spin orbit coupling is not monotonically varying, the effect of spin orbit coupling. So in this case, it will be hard for us to actually compare the how much defect induced spin orbit coupling is there. I mean, it is definitely there, but it will be hard to disentangle both the effects.
Okay, okay. Yeah, the damping also looks very high, no? Like 0.03
Yes.
is above
So
0.03. It's very
yes.
high. Hmm.
So damping in gadolinium-based materials, for example, I have also previously studied gadolinium ferrum, and in that alloy also, the damping is mostly close to 0.05 or 0.03.
Okay, okay, yeah, yeah.
Okay,
Okay, thank
so
you.
Thank you.
if there is no more questions, Sucheta, thank you once again. And we